Today we will do something called the Mathieu equation, which is a special case of Hill's equation. You will remember a problem we studied earlier, which was the vertically driven pendulum. We studied it for large theta. We studied it for arbitrarily large strong excitation here, and there was gravity. Of course, the gravity could be the other way or it could be turned off. If you look at that and you put theta small and c equals 0, no damping, in that case you will see that that equation can be written as theta double dot plus some number delta plus some epsilon cos t theta equals 0. This is Mathieu equation. Okay, and it is a special case of Hill's equation where Hill's equation is x double dot, let us say, plus p of t times x equals 0. There is no damping. P of t is periodic. So P of t is periodic, which means P of t plus capital T is equal to P of t for all t and some capital T greater than 0. All right. When we look at the fundamental solution matrix, we construct a solution x1 of t such that x1 of 0 equals 1, x1 dot of 0 equals 0. This is because we are thinking of the state vector q when we write it in first order form as xx dot. Okay. So x1 of t satisfies these conditions, x2 of t satisfies x2 of 0 equals 0, x2 dot of 0 equals 1. Then you will remember from our earlier discussion that the fundamental solution matrix is nothing but this matrix x1 of t, x1 dot of t, x2 of t, x2 dot of t. Okay, and then according to the classical theory of differential equations, there is something very interesting we do here. We calculate the determinant of this matrix. It's called the Wronskian. And the Wronskian is, what is it? It is x1, x2 dot minus x2, x1 dot. So far, basic, no problem. Now let us do something else. Let us, where were we? Here. Oh, the whole box is used up? No, well, we'll move here. Okay, so what we notice is that w dot, the rate of change of the Wronskian, is equal to x1 dot x2 dot plus x1 x2 double dot minus, just look at the Wronskian and it will be clear, x2 dot x1 dot x2 dot x1 dot minus x2 x1 double dot. Okay, now these terms obviously cancel and that leaves these here, but because this is Hill's equation, we have x1 p of t x2 with a minus sign. That's what this one is. This minus will become a plus p of t x2 x1, and so w dot is equal to 0. Because w dot is equal to 0, that means the determinant of phi of t equals constant. But the determinant of phi of 0 equals 1. That means the determinant of phi of t equals 1. Let lambda 1, lambda 2 be the eigenvalues. I'll remind you that phi of t, this phi of t is the monodromy matrix. Okay, so what does that mean? That means that lambda 1, lambda 2 is equal to 1. Okay, so either lambda is equal to sigma e to the power I, psi, and then lambda 1, and then lambda 2 would be sigma e to the power minus I psi, in which case lambda 1, lambda 2 is equal to sigma square, so sigma is 1. Okay, so in this case, we have lambda equals 1, and that's stable. Okay, but there is another case where lambda 1 and lambda 2 are real. So alternatively, or lambda 1 equals 1 by lambda 2, so this can be more than 1 and positive, then this will be more than 1, that means lambda 2 will be less than 1 and positive, or this can be negative and then that can be negative. For this reason, we should be able to draw the stability diagram, and I just need a small place to draw a circle for you to see. Let this be the unit circle. So either we will have eigenvalues like this, then we are stable, or we will have eigenvalues that come here, that is the border of stability. So I'll draw this with a cross and a square, I'll draw this with a cross, and I'll draw this with a circle. This is one case, this is another case, and this is a third case. Different possibilities. Now this can split and then go like this and like this. So one I'll show with a triangle and a triangle, and then this can split, and then I'll show one with a hash and with a hash. Okay, and therefore on a stability boundary, and I will clarify this here. So for example, we can think of delta and epsilon as making a parameter plane, and we can think of regions where it is stable and regions where it is unstable, and there will be a stability boundary. On such a stability boundary, we have to be either here with a red, let me mark it with a red, we have to be either here or here. That means that on a stability boundary, either lambda 1 2 equals 1 1 or lambda 1 2 equals minus 1 minus 1. Okay, so I have misjudged a bit. I have not taken enough space, so I'll have to get a new one now. Get a new one, not save the old one. Here is a new sheet. In fact, I should make it bigger. No, not that, this. Okay, so where were we? All right. So if lambda 1 2 equals 1 1, that means in fact that x is t periodic. Okay, so there is, wow, that's not strictly true. What I mean, there is a t periodic solution, and if lambda 1 lambda 2 is equal to minus 1, then we go from there is some initial condition x0, we map forward with time, we get minus x0, we map forward again and we get x0 again. So there is a 2t periodic solution. Okay, so this is true for Hill's equation in general, Mathieu equation in particular. And so something interesting has happened, which is that on the delta and epsilon plane, if we want a stability boundary, let us say there are stability boundaries, let us say it is unstable here, stable here, stable here. We are used to this idea, right? So over here, for example, when the forcing frequency is twice the natural frequency, right? So when we are looking at this equation, x double dot plus delta plus epsilon cos t x equals 0. So the forcing frequency is 1, that means natural frequency should be half. Okay, so for example, over here delta equals 1/4, we know that there is an unstable region here, right? We have done this analysis earlier, but there may be other stability boundaries. This one may extend like this. Okay, so this is unstable, this is unstable, there may be other unstable regions. We want to find them. We don't want to do a stability analysis on the whole plane. We will just look for delta epsilon curves on which there is either a 2 pi periodic or a 4 pi periodic solution. So our stability analysis just became much easier. Okay, so how do we think about that? If it's a periodic solution, we can think about it in terms of Fourier series. So let us think about it like this. Let us think about a 2 pi periodic solution. That means we have A0 plus the sum from 1 to infinity of ak cos kt plus the sum n from 1 to infinity of bn sin nt. This is Fourier series. Okay, now here is how we solve this. What we do here is we substitute this x into x double dot plus delta plus epsilon cos t x equals 0, and then we do harmonic balance. In principle, we balance all harmonics, so we'll get infinitely many equations. So that will lead to what is called the method of infinite determinants. But what we notice here is the reason I took cosine here instead of sine will also become clear. I could have taken sine and the stability properties are the same, but with cosine it is more transparent. So over here you see this part from all the sines, so I'll get cos t times sine nt, right? So cos t sine nt will give me something sine n plus 1 t, and now that's not what I wanted, plus something else times sine n minus 1 t. So the point being that in this expansion here, the sines, when I substitute over here, they give me sines only. They don't mix with the cosines. Okay, and similarly when I use the cosines, so when I write cos t cos kt, I will get something times cos k plus 1 t and something times cos k minus 1 t. In this way, you can see that, where am I? In this way you can see that these will decouple from these. Okay, so those are the 2 pi periodic solutions. How about the 4 pi periodic solutions? So when we look at 4 pi periodic solutions, then we should try something like this. We should say A0 plus the sum from k equals 1 to infinity of ak, and then I should write cosine of n t by 2 plus n equals 1 to infinity bn, sorry, this will be k, apologies, sine nt by 2. Let me check if I made a mistake here. No, that was okay. Okay, and here also something very interesting happens, because you see when we look at cos, when we do the harmonic balance, when we do cos t sine nt by 2, we get something sine n by 2 plus 1 t plus sine n by 2 minus 1 t. Okay, so the half integers remain half integers. Okay, so that is why we can come here, we can look at when will these be half integers, when n is odd. When n is even, these will become pure integers, that we have already got. Okay, so over here this will be basically k odd, this will be n odd. This part we just saw. Similarly, when I take cos k by 2 t times cos t, again I'll get half integers. Okay, this is why the search for periodic solutions using Fourier series decouples into 4 different problems. The search for periodic solutions of period 2 pi or 4 pi using Fourier series decouples into 4 problems, and we can look at these 4 problems one by one in the next lecture.